All right, so limits at infinity. So up to this point, we have been talking about the limit of a function at a given value. And now what we're going to do is see what happens when we evaluate limits at infinity. Okay, and basically what we're looking at is when x increases or decreases without bound. All right, so the way we determine limits at infinity is we're looking at end behavior. So we could care less what's happening in the middle. I don't care. What I'm asking is what's happening to the ends of the function's graph as x is either increasing without bound or decreasing without bound. So if we're looking at limits at infinity on a graph and we're given a function here that actually has two horizontal asymptotes, which we have not typically seen that much of. Most often when you guys were given a function you had one horizontal asymptote. This actually occurs when you have a radical in a function, and you don't see it that often, but it does happen. So when we're looking at finding the limit, in this case here, we're looking at the limit as x is approaching positive infinity. You're looking at the horizontal asymptote. So when I look at the graph right here, I'm looking at what is the end behavior of this function as x is getting larger and larger. And is my y value going to continue to increase? No. Actually, what does it approach? It does approach 2. Which more specifically in this case is the horizontal asymptote y is equal to 2. Okay, when you're answering these questions, you don't have to state what the horizontal asymptote is. I'm just letting you know that's what we're looking at. So then when we're looking at the limit as x is approaching negative infinity, your value is not always going to be the same. You have to look at the end behavior of the function, and in this case, the end behavior of the function as x is decreasing without bound. What does y approach? Negative 2, which is also another horizontal asymptote. Okay? All right, so we're going to talk about a couple different types of functions. In this case, we're going to start with limits of polynomials. This is why it's important that you know what parent functions look like. You need to know the graphs. So here, when we're looking at the end behavior of a polynomial, the end behavior is going to match the end behavior of the highest degree term. Okay, so what we're looking at is the end behavior of the highest degree term. Like I said before, we don't care what's happening in the middle. Just like if you have a polynomial that is a 5th degree, we know that we're going to have at most 4 terms. If you guys remember all that stuff from Algebra 2, we'll have a potential of 5 x-intercepts. Remember, you could have less because there could be imaginary. But the idea here is we don't care what's happening in the middle. What we're looking at is what are the ends doing. So when we're looking at this polynomial here, we're looking at the limit as x is approaching negative infinity. Okay? And we're looking at this right here. Okay? It's the highest degree term. It's not that these don't matter, but they are insignificant when it comes to end behavior. So these are insignificant to end behavior. Okay? So really, they just affect what's going on in the middle. So now, I just need to figure out what does an x cubed graph look like. Do you guys remember what it looks like? Yeah, it's like this weird kind of S shape, right? So it would look something like this. Okay. Now, does it necessarily go through the middle? Does it go through the vertex? I don't know. Do I really care? No, because it's not affecting end behavior. What I'm looking at is this part of my graph, because I want to know what is happening as x is going to negative infinity. So, as x is approaching negative infinity, what is f of x doing? Yeah, it's going to negative infinity. Okay? All right, so I take a look at this function right here, and I am looking at the highest degree. In this case, this function is not in standard form. So what is the highest degree term? The whole thing. The term. Not the degree, the highest degree term. Negative 5x. I heard some of you say it, but then all I heard was 6. So negative 5x to the 6th power. So we're looking at as x is approaching negative infinity. So I'm ignoring these terms right here, right? They are insignificant to end behavior. So for those of us that have forgotten, when you have an even degree, the end behavior mimics which most commonly known function? Yeah, a quadratic. So again, something's going on in the middle. That's this stuff right here. Don't care. I just want to know what's happening to the ends. So tell me a little bit about the ends of this graph. They're both going down. Exactly. Remember, the end behavior for even functions is the same. So it's either both up or both down. So if I were to sketch just a replica of the ends of the graph, I would have something like this. Now, why did I leave the middle open? I have no idea what's going on there, right? I just really care what's happening to the ends here. Okay, and more specifically, I'm looking at what is happening as x is approaching negative infinity, which is in this direction here. Okay, so as x is approaching negative infinity, what is f of x doing? Negative infinity. Now, is your answer always going to be negative infinity? No. It just so happens that these two are. Okay, questions on polynomials. Okay, so quick question. Did I cancel these out? No. What am I doing? Just ignoring them, right? They're insignificant to end behavior. And I'm asking you this because it's going to come up again later. And I had someone ask me yesterday, why did you cancel those terms out? Not canceling them out. Okay, so limits of rational functions. Okay, remember, a rational function is not a polynomial if there is a variable in the denominator, meaning a factor of some kind, x, x minus 2, x plus 3, whatever. So here, the technique in finding limits at infinity for rational functions is the same as finding the horizontal asymptotes for the rational function. Okay? So, for those of us that have forgotten, I am going to go over these rules in just a second. These are just example graphs right here. But a horizontal asymptote for a function f is a given line. Y is equal to 5, y is equal to negative 7, y is equal to 3/2, whatever. Okay, such that the limit as x is approaching positive or negative infinity would be equal to that horizontal asymptote. Okay? So that's what we're looking at. And here, again, this just says that a function could have at most 2 horizontal asymptotes, but we're going to take a look at how we find those in just a second. Anybody have any questions before we continue to the next page?